The pH scale gauges the hydronium ion concentration and reflects the degree of acidity or basicity of a solution. The pH scale ranges from 0 to 14, 0 being very acidic and 14 being very basic. The pH scale is somewhat analogous to the temperature scale used for assignment of relative levels of hot and cold. The temperature scale was developed to allow us to indicate how hot or how cold an object is. The pH scale specifies how acidic or how basic a solution is. And the formula that we use to calculate pH is equal to minus the log of the concentration of hydronium. It's important that you memorize this formula. Let's use the following bullet points to help us develop a further understanding of the concept of pH. The first one says, if I add an acid, I'm increasing the concentration of hydronium. Well, that makes sense. Hydronium is a strong acid. And if I'm increasing the concentration of hydronium, I'm lowering the concentration of hydroxide. Conversely, if I'm adding a base, I'm going to be increasing the amount of hydroxide and lowering the amount of hydronium. And when the concentration of hydronium and the concentration of hydroxide are equal, well, that's going to happen when I have equal amounts of acid and base present in my solution. What's important to remember is that in all three of these cases, that the concentration of hydronium multiplied by the concentration of hydroxide is always going to be equal to 1.0 times 10 to the minus 14, which is our kW value. Since the concentration of hydronium times the concentration of hydroxide is equal to a constant, 1.0 times 10 to the minus 14, and kW is the ion product constant for water. It makes sense that if I increase the amount of hydronium, that the amount of hydroxide is going to have to decrease. The converse is also true. How do we go about measuring the pH of a solution? Well, there's a few ways that we can do that. We can calculate the pH if the concentration of either ion is known, and what that means is if we know the concentration of hydronium or if we know the concentration of hydroxide. It can also be approximated using what's called pH paper, or sometimes indicator paper, that develops a color related to the solution of the pH. Then the color that you get is matched with the standard color chart. The color chart tells you which color represents which pH. You can also use a pH meter, which uses a sensor, which is essentially a pH electrode, that develops an electrical potential that is proportional to the pH of the solution. Let's go back to this first bullet point though. How would we calculate the pH of a solution if we knew either the concentration of hydronium or the concentration of hydroxide? Another question we could ask is, how do we calculate the concentration of hydronium or hydroxide when the pH is known? In order to answer these two questions, we're going to use these two facts. That our kW, which is 1.0 times 10 to the minus 14, is equal to the concentration of hydronium times the concentration of hydroxide. We're also going to use the formula pH is equal to minus log times the concentration of hydronium. Before we get into some calculations that involve pH, let us take a look at the rules for significant figures in pH calculations. And these rules are covered in the Acids, Bases, pH, and Buffers lab. If I have a concentration of hydronium, let's say that's 4.5 times 10 to the minus 3 molar. Well, how am I going to calculate the pH of that concentration of hydronium? I'm going to use my formula pH is equal to minus log times the concentration of 4.5 times 10 to the minus 3. When I punch that into my calculator, I'm going to round my answer to have two significant figures after the decimal place. So this is a rule you need to be aware of. The number of significant figures in the reported concentration is reflected by the number of net numbers after the decimal place. The same thing holds true in reverse. If you were given a pH of 2.35 and you were asked to calculate the concentration of hydronium from that, and we'll look at how to do that in a second, since there are two numbers after the decimal place, you report your concentration with two significant figures before the multiplication sign. Now let's say you are asked what is the pH of a 1.0 times 10 to the minus 4 molar hydrochloric acid solution? Well, the first thing you need to remember is that hydrochloric acid is a strong acid. And how would you know that? Because you memorized the list of strong acids. And what do we know about the dissociation of a strong acid? Not only does it dissociate, it dissociates completely. I'm not going to write the word completely, I'm just going to write 100%. So that means that when we take that HCl and we put it in water, it's going to dissociate completely. And that's what's meant by this irreversible arrow, or this one-way arrow. We're going to end up with hydronium, which we're interested in because we need to know the concentration of hydronium to calculate the pH. Plus, we're going to end up with chloride as well. Now, initially, we're starting off with 1.0 times 10 to the minus 4 molar HCl. And we have no hydronium and no chloride. But what's going to happen is all of that HCl is going to dissociate, and it's going to be a complete dissociation. So the change is going to be is that we're not going to have any HCl after the equilibration is done. So we're going to lose all of that. And since the stoichiometric ratio of HCl to hydronium to chloride is 1 to 1 to 1 in this balanced equation, I know that if I lose 1.0 times 10 to the negative 4 molar of HCl, I'm going to gain 1.0 times 10 to the negative 4 molar of hydronium. And the same thing applies for my chloride. So that means that at equilibrium, all I have to do is tally these numbers up. Now 1.0 plus negative 1.0 gives me 0, and the concentration of my hydronium is going to be 1.0 times 10 to the negative 4 molar. Now that's the only thing I'm interested in order to calculate my pH. So let's plug that into our formula. I'll write down my formula. pH is equal to minus the log of the concentration of hydronium. I'm going to plug that concentration from my complete dissociation into my formula, 1.0 times 10 to the minus 4. And when you plug this into your calculator, you get that the pH is equal to 4.00. And when you plug this into your calculator, you get that pH is equal to 4.00. Now what if I'm given the pH and I want to calculate the concentration of hydronium? Let's take a look at how we would do that. What is the concentration of hydronium of a solution with a pH of 6.00? Well, if we want to solve the formula pH is equal to minus log of the concentration of hydronium, we can rearrange it and solve for the concentration of hydronium. When we rearrange that formula, we get that concentration of hydronium is equal to 10 to the power of the negative pH. This is another formula that it'd be very wise for you to have memorized. At this point, it's just a matter of plugging the numbers into our calculator. But it's important that you realize that since I have 2 digits past the decimal place, I'm going to report my concentration to 2 significant figures and not 3. So when I punch that in my calculator, I get 1.0 times 10 to the negative 6 molar. The more practice that you do, the easier it will be to remember this formula. pH is equal to minus log times the concentration of hydronium, and the concentration of hydronium is equal to 10 to the power of negative pH. What if I wanted to solve this problem? What is the pH of a 1.0 times 10 to the minus 3 molar potassium hydroxide solution? The first thing you should notice is that potassium hydroxide is a strong base. What does it mean if potassium hydroxide is a strong base? It means it's going to dissociate completely. So when I take potassium hydroxide and I put it in water, it's going to dissociate completely into potassium ions and hydroxide ions. Now what information can we get from this complete dissociation? Well, if initially I start out with 1.0 times 10 to the minus 3 molar potassium hydroxide, what's going to happen is when it changes, what's going to happen is that when it dissociates, I'm not going to be left with any potassium hydroxide left over. So I'm going to lose all of my potassium hydroxide via dissociation, and I'm going to gain 1.0 times 10 to the minus 3 molar potassium ions and 1.0 times 10 to the minus 3 molar hydroxide ions. The net result, or final result, which I will denote with the letter F, is the sum of these. So 1.0 plus negative 1.0 means I'll have no potassium hydroxide left over. I'll have 1.0 times 10 to the minus 3 molar potassium ions and 1.0 times 10 to the minus 3 molar hydroxide ions. But again, I'm looking for the pH. And to solve for pH, I'm going to use the formula that pH is equal to minus the log of the concentration of hydronium. So how am I going to get the concentration of hydronium? Well, the good news is that we know that Kw is equal to the concentration of hydronium times the concentration of hydroxide, and that Kw is a constant, and we already know the concentration of hydroxide. So let's rearrange the formula and solve for the concentration of hydronium. So the concentration of hydronium is going to be equal to Kw divided by the concentration of hydroxide. Let's plug the numbers in. 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 3, and I get that my concentration of hydronium is 1.0 times 10 to the negative 11. Now I'm all set up to plug this concentration value into my pH formula. pH is going to be equal to minus the log of 1.0 times 10 to the minus 11. Notice again that in my concentration I have two significant figures. Therefore, when I report my pH, it's going to be 11.00 because I will report two decimal places. Let's try another problem. What is the concentration of hydroxide of a solution with a pH equal to 4.95? The first thing I'll do is I'll use my pH value to calculate the concentration of hydronium. And for that, I'll use the formula that concentration of hydronium is equal to 10 to the power of negative pH. So that's going to be equal to 10 to the power of minus 4.95. Notice that my pH has two decimal places, the 9 and the 5. Therefore, I will report the concentration to two significant figures. So it's going to be equal to 1.1 times 10 to the minus 5 molar. Again, this concentration is my hydronium ion concentration. From there, I'm going to use the formula Kw is equal to the concentration of hydronium times the concentration of hydroxide to calculate the concentration of my hydroxide. Let's rearrange the formula. The concentration of hydroxide is going to be equal to Kw divided by the concentration of my hydronium. So I have 1.0 times 10 to the minus 14 divided by 1.1 times 10 to the negative 5. When I punch that into my calculator, I get the concentration of my hydroxide is equal to 9.1 times 10 to the minus 10 molar. This makes sense because a pH that's less than 7 is acidic. Therefore, a pH of 4.95 must be acidic. And based on our Kw, which is 1.0 times 10 to the minus 14, at neutral pH, meaning a pH of 7, both the concentration of the hydronium and the hydroxide would be 1 times 10 to the minus 7 molar. So, the fact that the concentration of hydronium is greater than 1 times 10 to the minus 7 molar makes sense, and therefore the concentration of our hydroxide will be less than 1 times 10 to the minus 7 molar. This figure shows the pH scale. It's important that you understand that the lower the pH value is, the greater the concentration of hydronium. Here they've written H+, but H+ is another way of representing hydronium. So again, as the pH decreases, the concentration of hydronium is going to increase. And since our Kw is a constant, and that's equal to the product of the concentration of hydroxide times the concentration of hydronium, therefore, when the concentration of hydronium is large, the concentration of hydroxide will be very small. The opposite holds true as well. When we have a very basic solution, the concentration of hydroxide will be very large, and again, based off of Kw, the concentration of hydronium will be very low. A pH of 7 is neutral. This is where the concentration of hydronium and the concentration of hydroxide are equal to each other. Something else you might have noticed is that each tenfold change in concentration changes the pH by 1 unit. For example, if we go from a concentration of HCl that's 1.0 times 10 to the minus 2 molar, and we increase it to 1.0 times 10 to the minus 1 molar, we're increasing the concentration by tenfold. And when we do that, our pH decreases by 1 unit. Another way to say this would be, if I'm decreasing the pH by 1 pH unit, I'm increasing the concentration by tenfold. So let's say you're going from a pH of 6 to 4. What are you doing in terms of concentration? Well, you're increasing the concentration tenfold here and tenfold here. So overall, you're going to have a concentration that's 100 times stronger.